Welcome to this Tech Talk Live today on Unvented Hot Water Safety and Control. I am Paul Harmer and I'm the Technical Director of the CIPHE. I'd like to hand over now to one of our industrial associates, Altechnic Limited.
Welcome to Tech Talk Live on Unvented Hot Water Safety and Controls. My name is Martin Frost and I am an OEM Sales Manager for Altechnic. With me today is a colleague, Steve Elsmore. He's an Altechnic product specialist. Altechnic were formed in 1988 and we are part of the Kalefi Group. We are one of the largest UK manufacturers of quality plumbing products, such as thermostatic mixing valves, thermostatic radiator valves, pressure reducing valves, and of course, unvented safety controls. Steve is a time-served engineer, and myself, I'm G3 qualified. I'm also qualified in central heating and hot water electrics and backflow prevention, which are all key components of unvented cylinders. The first product we're going to talk about is inlet groups, sometimes referred to as combination valves, which will become apparent as we go through it. Inlet groups come in multiple configurations, from 22mm one piece right the way up to 2-inch 3-piece units, and we do domestic and commercial installations. So, inlet groups, the very first thing that we would point out is the arrow on the valve. Sounds obvious, but we get called out to systems that don't work correctly, and one of the problems that we encounter is that somebody has piped up the valve in the wrong direction. So the arrow, please follow the arrow. The flow of water going through the valve has got to be in the direction of the arrow. Okay, let's concentrate on the 22mm domestic inlet group. These units have 4 main components, but most of them will also have a few extras, such as cold water balance takeoff and a vessel connection takeoff. So the first main component that we're going to talk about is the strainer. The strainer is there for 2 reasons. The first one is to actually take out any debris in the upstream flow. It also then protects the main component parts on the product of the downstream flow. The second item is the pressure reducing valve. The pressure reducing valve is there to actually steady the pressure and maintain a constant pressure downstream, because upstream you don't know what the pressure is going to be. And throughout the UK it will vary quite considerably, from less than 1 bar to anything up I've heard in parts of the country it can be 15 or 16 bar. So 3 bar, 3.5 bar are the common pressures in the UK of pressure reducing valves for unvented cylinders. Third component is the single check valve. The single check valve is there to stop gravitation of potentially dangerous warm water mixing with your cold water circuit. The fourth element is the safety relief valve. The safety relief valve is there to actually protect you from pressure, excess pressure in the system. If something were to go wrong, this is the first safety port. If the pressure increases beyond the set point, which common is 6 bar, then this will open up and relieve that potentially dangerous pressure. 6 bar is also common. You get 8 bar, they do vary, but as soon as that system reaches the set pressure, it will relieve it. Moving on then from inlet groups, the next product that we're going to discuss are temperature and pressure relief valves. Temperature and pressure relief valves then do exactly what they suggest. They safely control the temperature and the pressure. Temperature and pressure relief valves, just like inlet groups, come in wide and varied configurations. They come in 1/2 inch, 3/4 inch, etc. sizes. They come with standard and longer probes to basically suit the application that they're meant for, and they come in varying connections. In the UK, temperature and pressure relief valves have to be fitted at site of manufacture. Every unvented cylinder that's supplied into the UK has the temperature and pressure relief valve fitted. Temperature and pressure relief valve is there for two reasons, as we stated. One is pressure. A lot of these are actually set at 6 bar, some are 8 bar, some are 10 bar. That then protects the cylinder specifically from overpressure. If a fault occurs in the system in some way, shape or form and everything else fails, the pressure in the cylinder will quite obviously rise. As it rises, it'll get to the set point of the temperature and pressure relief valve, in this case 6 bar. As it hits 6 bar, the temperature and pressure relief valve will open and it will relieve that pressure safely. The second function of a temperature and pressure relief valve is the temperature. This is the last line of defence if all the other controls fail and the cylinder starts to heat up. As the cylinder starts to heat up more and more and more, it will overcome all of its safety controls until it starts reaching 90 degrees centigrade. Once it starts to reach 90 degrees centigrade, the cylinder becomes very, very dangerous. Temperature and pressure relief valve then will start to open at 90, and as it approaches 95 it will fully open and it will discharge most, if not all, of the cylinder's capacity of hot water, thereby releasing the safety factor. Now that we've talked about inlet groups and temperature and pressure relief valves, if a problem occurs in the system, they have to discharge somewhere. And again, in G3 regs, it's set down and laid out fully for you to follow. P&Ts, they come in the various sizes that we've discussed. The outlet of this one is 15mm, as an example. 15mm outlet, you have to go into a 15mm inlet of a ton dish. A 2-inch outlet of a P&T will have to go into a 2-inch inlet to the ton dish. That follows suit, but where it slightly differs is that every ton dish, no matter what the entry size, you have to go up one size and the exit. So a 15mm ton dish will actually have a 22mm outlet. A 22mm ton dish will have a 28mm outlet. A 2-inch ton dish will have a 2.5-inch outlet. Again, it all follows suit. That's all laid down in G3 regs for you. The ton dish then is a backflow prevention device. It is also a visual port for you to see what's happening when the units are discharging. It will tell you, almost tell you, exactly what the fault may or may not be. Sometimes you'll see it dripping, sometimes you'll see it gushing. That will indicate the fault for you to do further investigation. Now that we've dealt with the discharge D1 and D2, we can now move on to expansion vessels. Expansion vessels does tend to cause us one or two issues, in as much as people, because they are cheaper, will fit heating vessels where they're able to. Heating vessels are prone to rusting very, very quickly if you put them on an unvented cylinder. You have to use a potable vessel. A potable vessel is different from a heating vessel in as much as the water doesn't touch the inside of the vessel in any way, shape or form. It is contained within a bag or a membrane, thus protecting the vessel doesn't rust. The other aspect that we come up against is pressure. Pressure. We've touched on the inlet groups. The inlet groups can be 3.5 bar in a typical domestic installation. Whatever that pressure is, you must marry it up to the pressure of the potable vessel. So if the inlet group, pressure reducing valve of the inlet group is 3 bar, the pressure in the potable vessel must also be 3 bar. If it falls outside either higher or lower, it will manifest itself in a leak, probably a drip that you'll be able to see at the ton dish. And that's probably coming more often than not from the safety relief valve of an inlet group. Potable vessels just like all the other component parts that we've discussed, comes in various sizes and various connections. You can have compression, as an example. They will also all come with a Schneider valve. Schneider valve is there to actually release pressure or pump up the pressure to match the pressure of the inlet group that we've just talked about. So, now we've talked about most of the mechanical products, we now have to move on to the electrical products as outlined by G3. In the arrangement of the electrical controls, they also have to follow Part L regulations. Now, Part L states that if there is no demand for either time or temperature, then the boiler and pump mustn't come on. This also follows suit within these. If there's no demand for time or temperature, the boiler and pump can't come on, but they're also governed by Part G. Part G, safety. First one that we're going to talk about is the dual thermostat. A dual thermostat has two thermostats. One is a high limit and the other is the control. The high limit is just about always set at 82 degrees centigrade. The control speaks for itself. That's the part that you actually set for the comfort of the customer. If the high limit stat fails and the control stat fails, the temperature of the cylinder will rise and rise and rise, and it will actually start reaching the temperatures of 90 plus. That's when the pressure and temperature relief valve comes into play. It will also open up if these units fail. So a dual thermostat has to be connected to a zone valve, and in this case, on this particular cylinder, this is a 22mm unit. So you have time and temperature requirement, both control and high limit stat is calling. That will then open up the motorised valve. As the motorised valve gets to fully open, it will connect the end switch inside it, and that will bring on the pump and boiler. Pump and boiler is running happily away, and then the internal temperature of the water will obviously rise. That will rise to the set point of the control stat. Let's assume it's 60 for the moment. As it hits 60, the stat will become satisfied. Terminals will break contact within the stat. The boiler and pump will go off. As I just mentioned, if that stat fails in any way on, the temperature will rise, the internal temperature will continue to rise, and that will reach very soon 82 degrees centigrade. As it hits 82 degrees centigrade, then the high limit stat will become satisfied, and that will break its contacts, and in the same event it will turn off the pump and boiler. If by some extreme issue, which very, very rarely happens, and both of these stats fail in the on position, then the temperature will continue to rise, and of course it will raise to the temperature which will then set off the temperature and pressure relief valve.
Well, it was excellent listening to Martin Frost of our Technic, talking about the different safety components of an unvented hot water cylinder. I'd like to ask a question to Steve, product specialist. Maybe incorrect pipework installed. What do you think could happen? Any examples of any problems?
Okay. First of all, we've got an installation here that we mocked up earlier. It's important when looking at unvented cylinders to maintain them on a regular basis. Most manufacturers will dictate that they're maintained at least once every 12 months. And things like pipework installation are key when looking at your maintenance. So we're going to go have a look now at one we've put together here. First of which is the inlet control group. Now, as Paul quite rightly questions, if they're incorrectly piped up, you get all sorts of different issues manifesting over the years. Firstly, we're going to have our cold main come into our pressure reducing valve. Chief function, of course, to control the pressure going to our main cylinder. Now, if the pipework doesn't come in on the inlet side, as daft as that sounds, it can cause all sorts of issues. So we have had cases where people have brought in the mains into the balance port connection and capped off the cold mains in. This of course means then that the pressure is not controlled and can cause the safety relief valve to lift, which you'll see through the tundish once again. One of the other questions we get asked quite regularly is, what happens if I put a check valve here? Well, that then stops our expansion vessel from working. We have a clear path. Our pressure reducing valve controls the pressure, water comes in, is maintained through the check valve and into the cylinder, out to our taps through the hot water outlet. When this is heated up by our coil, flow and return, that we then get heat gain in the cylinder, the water becomes bigger, the volume expands, comes back through this pipework, hence the check valve, and through the vessel connection into our expansion vessel. Once this is expanded, you get full operation of the system. In the event that you put a check valve here for some strange reason, the water cannot expand up to its expansion vessel. Yet again, our safety relief valves start to do their job. Of course though, this one isn't being operated. It's our temperature and pressure relief valve that sees the event, and you'll once again get discharged through the tundish.
Okay, so that's a few things on pipework. What about check valves, maybe?
So as we just mentioned, if you install a check valve here, you're going to get issues. Putting a check valve on the hot, on the outlet, we've seen that on a couple of occasions. Once again, it can cause you damage. And we've even seen check valves installed on the discharge pipework, which of course is a big no-no.
So the key thing here, which the CIPHE would like to emphasise, is you must annually maintain your unvented hot water system.
Correct.
Would you agree?
Yeah, correct. Key things, installed in the correct manner. So we've picked up on pipework, vessel installation and check valve installation. And then once you're installed and your system is operational, maintaining it as you would your car every year is key. So expansion vessels have an air chamber in them. If this isn't correctly maintained, the volume of water is more readily accepted by the vessel, or indeed not accepted by the vessel, once again causes safety relief valves to wear. So a very common issue we have, Paul, is that people will call our technic for advice. They'll say, this is the second or third safety relief valve I've changed, and their initial reaction is always to blame the component.
Yes.
In fact, what they're probably looking at is a system that's been poorly maintained. So you've got a system where the vessel pressure hasn't been checked for maybe a year, 2 years. As you said, if you quite rightly point out, it's checked every year and maintained, then you're not going to get the wear on components. Those valves are designed to do a job, and when they're lifting, they're telling you there is something wrong with the system.
Okay, so these need to be charged and checked every year.
Correct, yeah. Of course, the data plate for that is always on the vessel. In this case, it's on the top. But a clear indicator is usually the cylinder manufacturer's handbook, which should always be left with the equipment.
Okay, well, thank you very much. So I'd like to ask a couple of questions about the vessel.
Okay.
So, first one is the type of expansion vessel.
Yep.
Do you want to just tell us a bit more about the issues of an incorrect expansion vessel?
Okay, so standard installation such as the one we have here, your vessel will be a potable vessel, usually connected via a tapping on the inlet control group. Here is used with a flexible hose. Some indication of installation is exactly where they're picked up on the inlet control group. But as you quite rightly say, Paul, it should always be a potable vessel. If you install the vessel incorrectly, so the wrong side of the check valve, for example, we've had people install it on the balance port, it cannot function. Once again, you're going to see your alarm bells, your safety relief valves discharging. I mean, we've dealt with several issues over the years from people having orange water coming out of their taps, and one of the clear indications of that is that they've put the wrong vessel on. So the vessel, for some reason, has failed, and they've replaced it with a central heating vessel.
Right, and that's clearly the key thing here to point out is the white potable expansion vessels, which are critical, aligned on the inside to stop the water from coming in contact with the metal, which causes it to rust.
Yeah, as you quite rightly say, the water is maintained and kept within a bag. This one we've done a quick cutaway so we can see. There is a membrane bag that the water is kept maintained within, whereas a heating vessel, they have a diaphragm so that the water is kept physically within the metal chamber. Now, of course, in a heating system, the water isn't changed as regularly, so therefore it doesn't rust as often. Whereas if you put a heating vessel on a potable circuit, you're changing the water rather on a daily basis, and it rusts.
So tell us a little bit about the pre-charge.
The pre-charge effectively is your air chamber that surrounds this membrane. Now, when the vessel is in the static position, your pre-charge is similar to your inlet control group pressure. So this, in this case, is a 3-bar valve. The air chamber in here will be 3.2. So when this begins to heat, this air chamber is crushed by the water expanding. So it takes up the heat expansion from the cylinder. Now, if that vessel pressure isn't maintained, once again, like your car tyres, you'll find it goes flat over time. It needs to be maintained to stop your safety relief valves from reacting.
Maintenance is key. It is really key, I believe.
Yeah.
Every year, with such a, it's a simple product for what it does, but there's these key safety features we must not overlook. So we've heard quite a bit about the other features and the safety features, more recently the expansion vessel. I'd like to ask Steve a question about the discharge. So we're looking at the ton dish. So Steve, any issues that could cause the ton dish to demonstrate or show water coming through?
Okay, so the ton dish is our main communication port. Any of these two valves could potentially discharge, and this one could potentially discharge at 90 degrees of water at full flow. So it's important that these are routed correctly. You'll see in this installation we have a soil stack in the corner, and you'll note that this isn't piped into that soil stack. Now, plastic soil stacks have a temperature rating, so there's a reason in G3 this demands the discharge D2 be piped to an external drain where safe and appropriate to do so. In some cases that involves even putting a wire cage around the discharge to stop children's fingers or pets getting near the potential 90 degrees of discharge. Now, looking at the reason why that may discharge, we're back to looking at our whole system. Bearing in mind that this is always just a communication window, it's telling us something's wrong. The fault generally ever is not the TMP or the SRV, they're warning signals. Something's caused that valve to open and to do its job. Now that could be the pressure reducing valve has failed, or the expansion vessel itself, the air charge has perhaps dissipated and therefore isn't enough room for the system to physically cope with the volume of expansion. Therefore the TMP will lift or the SRV will lift, and a clear telltale sign is water through that ton dish.
I'd like to thank our Technic today for this Tech Talk Live on the safety and control of unvented hot water systems. It's at the core of the CIPHE's values for safety and the health of the public. So thank you Martin and thank you Steve.
Thank you.
I'd like to thank our Technic Limited today for an excellent Tech Talk Live on unvented hot water safety and control. The CIPHE would like to point out 3 key areas. Number 1, qualification. Always ensure, whether you're installing or maintaining an unvented hot water system, that you are qualified and competent to do so. This means you must adhere to the Part G3 of the building regulations. Number 2 is maintenance. This system is not a fit and forget product. It must be maintained annually to ensure all components are operating safely. And the third point is compliance. Make sure that your product that you are fitting is RAS approved and is acceptable to be installed in the United Kingdom.